All right, so for today, my last lecture, basically I'm going to solve a problem which is multi-mode heat transfer. So basically it's radiation with something else, either conduction or convection, so it's not just radiation only. Okay, so let's jump into it. We have a 1 meter high by 2 meter wide solar collector. So down here is the image of the solar collector right here. That's our solar collector. It consists of an absorber plate and a cover plate. Well, the absorber plate is color-coded red right here. You can see it. And the cover plate is just to cover it right here. And so the goal of the solar collector is to gobble up all those solar photons, make it some fluid hot that's in the solar collector and the absorber plate. Maybe a water or some other glycol, something that won't freeze on a very, very cold day in your roof. Because if you run water through it and then you have a very cold night, in the middle of the night it might freeze. So a lot of times they have some glycol solution. It's inclined at 45 degrees relative to the horizontal. So here's the angle, 45 degrees, and the whole assembly of the cover plate and absorber plate are tilted at that 45 degree angle. There's a 4 centimeter spacing between the plates. So this gap between the cover plate and the absorber plate is 4 centimeters. The cover plate, just to let the photons in and not have a lot of convection or wind taking away the energy. The absorber plate is going to be the hot plate. Okay. The solar radiation is 1,000 watts per meter squared. We'll use the symbol G for solar, G sub S, solar irradiation, 1,000 watts per meter squared. Now, what is that per meter squared? What area is that? It's the area that's perpendicular to the direction of the incoming solar irradiation. So you put your area like this to collect the maximum amount. So the maximum solar intensity is so many thousand watts per meter squared. True? So that's the area perpendicular to the direction of the incident solar radiation. The sun is at an angle of 60 degrees relative to the horizontal, so they're not coming in straight down. They're coming in at that angle of 60 degrees. Okay. Now the cover plate is transparent to solar radiation, and the solar radiation essentially is everything below around 3 micron. That's most of it. If it's not transparent, then it's what? Opaque. So it's transparent to solar radiation less than 3 micron, and it's opaque to longer wavelengths. What does that mean? Well, if there's a wavelength that's coming at the cover plate that's 5 micron, it's not going to make it through. It's either going to be absorbed in the cover plate or reflected off the cover plate, depending on the emissivity of the cover plate. True? So you have to read each sentence about 2 or 3 times to understand the problem. Both the cover and the absorber plates behave as gray diffuse surfaces with spectral absorptivities as shown. So here is the spectral absorptivity. What does that word spectral mean? It's described as a function of wavelength, isn't it? So as a function of the wavelength going out from 0 out to 5 and beyond, the cover absorptivity is 0. Hey, that's because it's not absorbing, it's not reflecting, it's transmitting all of that solar radiation. This is a great cover plate. All the solar radiation is just transmitted through that cover plate. But then at 3 microns, there's just a step function. And now, what is the absorptivity? 0.8. And out in this region, it's opaque. And in this region, it's transparent. Okay. So let's try and get this down in our minds. We know that the transmissivity plus the reflectivity plus the absorptivity is equal to 100%. In this region right here for the cover plate, in the solar region, from 0 out to 3 microns, what is the value of the transmissivity? 1. What's the value of the reflectivity? 0. What's the value of the absorptivity? 0. Now shift gears. You're still talking about the cover plate. Now talk about the longer wavelength. So does the equation that the transmissivity plus the reflectivity plus the absorptivity, does that still equal to 1 at those wavelengths? Yeah. And so what is the transmissivity of an opaque cover plate? Now it's 0 in this region. What is the reflectivity? Well, let's jump to the absorptivity and then come back to the reflectivity. What is the absorptivity in that wavelength? 0.8. True? 0.8. And now you can see what the reflectivity is. What's the reflectivity? 0.2. 0.2. Yeah, it's like a glass. And this is a made-up problem, but this would be a nice cover plate, wouldn't it?
Yeah. My question is, I know in glasses it's a volumetric process. Would you contribute to surface?
Right, and so what you have is a beam length, and it absorbs as it goes through that transmittance. So yes, it's a participating medium, that cover plate, and you would have the thickness, and it would be a much more challenging problem. But we're just going to treat it very, very simply, approximate right here. Now let's talk about the absorber. So the absorber between 0 and 2 microns, that's part of the solar radiation. It's a large part of the solar radiation. What is the absorber? First of all, the absorber is always opaque. There's no transmittance through the absorber. So it's either absorbed or reflected, true, for the absorber? So in this region, the absorptivity, well, the reflectivity plus the absorptivity is 100%, and the absorptivity is 0.9. So the reflectivity is 0.1. And then out in this region, from 2 and beyond, it's still opaque. The absorptivity is 0.3. 0.3, right? And so it's 0.7 for the reflectivity. All right. We understand now more about this information given the spectral absorptivities. Is it true if somebody said, I want you to give me for the cover the emissivity of the cover at a particular wavelength? Let's say the wavelength is 2 microns. Can you tell me what that emissivity is? 0. Because Kirchhoff's law, emissivity is absorptivity. How about they say it's at 10 microns? What is it now at 10 microns? The emissivity. Is it 0.2 or 0.8?
The emissivity is, it's absorbing at 0.8, but it's going to be, that means the balance is big.
Well, from Kirchhoff's law, the spectral emissivity is equal to the spectral absorptivity at every wavelength. True? And so this is going to be 0.8. Makes sense? Yes? Hopefully it makes sense. All right. So don't forget Kirchhoff's law, because somebody may say, I need the emissivity. It's equal to the absorptivity at that wavelength. All right. So part A, calculate the rate of solar radiation absorbed per unit area of the absorber plate. So it's not per perpendicular area of the incident solar radiation, it's per area of the absorber plate, right? So first of all, we have to do some geometry, don't we? And let me try and draw it right here. Let me draw a line straight across here. And think about this is the cover plate. And just translating the angle up, what angle is that with this cover plate and the horizontal? Isn't that 45 degrees? The same angle, right? 45 degrees. 45 degrees. If I come out and I go perpendicular to the cover plate, that's trying to show a little square in there, perpendicular. What is this? Well, that's 90 degrees, isn't it? That's 90 degrees. So now, what is the angle of the normal or perpendicular with respect to the horizontal, this side right there. What is that angle? It's 180 minus 90 minus 45, which turns out to be 45. So it's 45 degrees, 45 degrees. And the solar is coming in. I'll try and color code it like this. Isn't that the direction it's coming in? It's coming in with respect to the horizontal 60 degrees. So what is this angle right in here? It's 15 degrees, isn't it? So right away, the solar's coming in. If I had the area here, it would just be 100% one-to-one area, the solar incident area to the collector area. But if I say the rate of solar absorbed per unit area, it'll have G solar absorbed is equal to the G solar incident times the cosine of an angle that's between the normal of the surface going out, that's this angle right, this perpendicular coming out, and the angle of the incident coming in, which we just calculated as 15 degrees. True? And the cosine of 15 degrees is close to 100%. Yeah, 0.966. So it could be that you have 1,000 watts per meter squared, and if it's just going to, everything would go through the cover plate and be absorbed, then you would have 966 watts per meter squared. But not all of it's transmitted, and of that's transmitted, not all of it's absorbed. So now we're going to continue this with the characterizing the spectral characteristics of what is transmitted. So we're going to consider bands of wavelengths. And so 3 bands look normal for breaking this problem up. Can you see what the 3 wavelength bands would be for this problem? It would be 0 up to how many microns? 2 microns. Another band would be 2 to 3 microns. And the other band would be 3 out to infinity. So what we want to do is we want to find the fraction of the solar radiation that's coming at it in the 0 to 2. We want to multiply that by how much is transmitted through the cover times the fraction that's absorbed in the absorber. We find that fraction that's from 2 to 3 that's transmitted through the cover and absorbed in the absorber. The fraction of solar that's in the micron 3 plus that then is transmitted through the cover and absorbed in the absorber. You see how we have 3 bands and we're summing it up? All right. Let's, which ones are going to be the easier? The absorptivity of the solar? What's the absorptivity of the solar, the absorber in the 0 to 2 micron range? 0.9. What's the absorptivity in the 2 to 3 micron range? 0.9. And then the last one, the absorptivity, oops, this is 0.3, isn't it? 0.3. And then it's 0.3 from 3 out. True? So the absorptivities of the absorber, pretty good. We got that down. Let's now do the transmissivity of the cover in the 0 to 2 micron. 1. What's the transmissivity of the cover in the 2 to 3 micron? 1. And the transmissivity of the cover in the 3 and beyond? 0. So those are the easier ones to decipher. Now what we have to do is we have to go get the fractions of the radiation. How am I going to get a fraction of solar radiation that's 0 to 2 micron? How are we going to now calculate this quantity right here? Yeah, we're going to have to use the table. So we know that that table allows us to calculate the fraction of the radiation that falls between 0 and up to a specific micron. The index is the product of lambda t. So the lambda of interest for the first part is a 2 micron. And then what is the effective temperature of the surface of the sun that's throwing those photons out? 5,800 Kelvin. And so we're looking for lambda of 2 times 5,800, 11,600 micron Kelvin. It falls right in here. And we do a little linear interpolation, 0.941. 94.1% of the solar radiation's less than 2 micron. Then might as well, while we're in the table, look at the 3 micron times 5,800 Kelvin. That gives us a 17,400 micron Kelvin. It's in between these two values, linear interpolation, and we find that that fraction is 0.979, so almost 98%. So if we did this, let's just go ahead and do the fractions. The fraction from 0 to 2 micron for solar is 94.1%. What is the fraction from 2 to 3? You see, they take the difference of those two numbers, right? And when you take the difference of those two numbers, it comes in at 0.038. And then what's the fraction 3 plus micron? Wouldn't it be 1 minus 0.979, which comes in at 0.021. So around 2.1% longer, 3.8% in that band, and then this is 94.1%. If you add those three fractions up, double check yourself, you get 100%. That's a lot of work, right? You able to get that correctly? So now we can go back and we put the 0.941 there. We put the 0.038 there. And we put the fraction there of 0.021. And when you sum them up and multiply by that, what you find is that it's going to be gobbling up 84.68 or 84.69% of those in that waveband will make it through the cover, impinge on the absorber, and be absorbed in the absorber. And then here you get that it's the 0.01133, and then here. Then you add those up, multiply by the cosine of 15 degrees, multiply by 1,000, and we get the final answer that the solar absorbed flux on the absorber is 829 watts per meter squared. So roughly 83% that impinges, gets absorbed. Well, that's now expressed per unit area of the absorber. Isn't that the per unit area of the absorber plate? Yeah. All right. Well, that's part A. Any comments or questions on part A? Let's move to part B. So part B says the absorber plate is well insulated on the back side, and the cover plate temperature is 32 degrees C, and the absorber plate temperature is 77 degrees C. And now they want to say, what is the heat loss per unit area of the absorber plate? Well, where is it going that it's considered a loss? Is going, to where you not want it to go. Basically, you're running fluid through there, and it's removing some heat with the fluid that's coming in cold and going out hot. But at steady state, the absorber plate with this fluid in it's pretty warm, and you have a colder cover plate. So how is it being lost? It's not being transferred in this direction because it's well insulated on the bottom of that absorber plate. Yeah, so it's going in that direction. They want you to calculate the flux, heat flux, per unit area of the absorber plate going from the absorber plate to the cover, that way. Okay, so that's what we're being asked to, this loss. How do you calculate that loss? What are the mechanisms by which heat is transferred from the warm absorber plate to that cover plate? Because they give you both the temperatures. If they didn't tell you the temperature of this one, but maybe they gave you a convection coefficient on the outside and the temperature on the outside, well, then you'd have to actually calculate the temperature of the cover plate. But they made it a little easier by telling you the temperature of the cover plate. So what are the two mechanisms by which heat is transferred from the warm absorber to the cover plate? Yeah, Q double prime radiation and convection, Q double prime convection. In this gap, there's air, and it's not stressed here, but what you would just say is the pressure of the air between the cover and the absorber plate, 1 atmosphere pressure. You'd have to have it sealed, and then you would pull a vacuum, and then you'd have no convection losses. That would be great for heat transfer. You could knock that out. And maybe with this calculation, you'll say, well, let's just let it be air and let it be at 1 ATM. That's pretty easy to do. You don't have to seal it. You don't have to pull a vacuum. And see how much loss is due to the convection before I invest a lot of money to seal it and pull a vacuum. It'd be a better collector, wouldn't it, with no air in there? Well, how do we calculate both of these components? What about the Q double prime rad? Yeah, it's a difference in the black body emissive fluxes that drive the flow. And you can think of driving the flow through how many radiative resistors. So if I went back here, I would blow it up. I'd put here, this is the absorber plate, this is the cover plate. And I know the temperatures of both of those, temperature cover, temperature absorber. Hence I can get EB of the cover and EB of the absorber, the black body emissive fluxes. So help me with 3 resistors for the radiative transfer between those two surfaces. Wouldn't they be something like 1 minus epsilon over epsilon A out to a J of the cover, 1 over AF, and then to the J of the absorber, and then 1 minus epsilon over epsilon A for the surface resistance of the absorber. Would that look reasonable? And when you have something like this that has the same area, all these 3 have the same area, then if you haven't seen this done, let's go ahead and do it. EB of the absorber minus EB of the cover, we're going to have 1 minus epsilon of the absorber, epsilon absorber area, plus 1 over area view factor, plus 1 minus the emissivity of the cover over the emissivity of the cover A. All those 3 areas are the same, aren't they? And so you just bring that area out, or you could put it as Q over A, and now it's the flux that I want. Okay. And then we have EB absorber minus EB of the cover. But we have this 1 minus epsilon A, and you just divide by epsilon A and then put over epsilon A, plus 1 over the view factor, plus 1 over epsilon cover, minus epsilon cover over epsilon cover. So this turns into 1. This turns into 1, isn't it? And we have, I'll clean this up just a little bit, 1 over emissivity absorber minus, and so this one cancels with that one, and you're left with a much simpler result that the heat flux, let's just put it as Q double prime radiative, is equal to EB absorber minus EB cover divided by 1 over the emissivity of the absorber plus 1 over the emissivity of the cover minus 1. There's just a few steps to move into that simple equation. True? And now you think to yourself, okay, go back to this problem and say, what is going to be the emissivity, effective emissivity of the absorber? Well, what is the temperature of that absorber plate? It's 77 degrees F, which comes in at 350 Kelvin. It's not that hot. I mean, it's warm, but it's not like the temperature of the sun. So most of the radiation that's being emitted is being emitted at what wavelengths? Long wavelengths. It's out in the IR. Am I going to be able to see any of that emission? Not with my naked eye, no. With the IR camera I can, but not with the naked eye. I only see 0.4 to 0.7 micron. So it's not emitting in the short wavelength, it's all emitting in the long wavelength. So what would be the effective emissivity of the absorber? Point three. And then what about the emissivity of the cover? Well, at that long wavelength, the cover is not transparent. It's like an opaque surface. And so it's the emissivity is equal to the absorptivity. And so what's the emissivity of the cover? 0.8, isn't it? That makes sense? Give me a thumbs up if you're with me. Okay, good. So what we do is you have the 0.8 and whatever that was, I even forgot, 0.3 and 0.8, and you calculate that the radiative flux comes in, let me put it over here, at 100.5 watts per meter squared. So that's half of the problem. What about the convective flux? How are we going to calculate the convective flux? Any ideas? Yeah, it's natural convection in an enclosure that is hot on one side, cold on the other, and it's tilted a little bit. It's tilted. And so what you have to do is you have to say, okay, I'm going to be looking for a Nusselt correlation, which is a function of the Rayleigh number for a tilted enclosure. Okay. Well, we calculate the Rayleigh number, and it's based on the gap thickness L. What's the Rayleigh number? G beta delta T L cubed over nu alpha. And you calculate the thermal physical properties of air 1 atm at some average temperature. Well, it's working in absolute Kelvin. The hot surface of the absorber is 350 Kelvin. The temperature of the cooler cover is 305 Kelvin. So you calculate the average temperature of 327.5 Kelvin. You can get then the beta 1 over T average. So we get this property. What was the name of beta? Yeah, volumetric expansion coefficient, true? Okay, and for an ideal gas, like air, it's 1 over the absolute temperature. Okay, then we go ahead and get nu at that average temperature of around 330 Kelvin, 1 atm pressure. The value for nu comes in at 18.5 times 10 to the minus 6. Do you remember the units on nu? SI units? Yeah, meters squared per second. And then alpha, well, that's calculated to be 26.3 times 10 to the minus 6 meters squared per second. So we get the beta, we get nu, we get alpha. G, 9.81. The delta T is that difference. What is it, 45 Kelvin? And the L here, was 4 centimeters, 0.04 meters. So you calculate the Rayleigh number for that enclosure, and the Rayleigh number comes in at 1.78 times 10 to the 5th. And then you look for a correlation. Well, this correlation that you would want to use is for a tilted enclosure. And in our textbook, it's equation 954. It's tedious because it's so long, but you can put in the Rayleigh number. You check that the aspect ratio for this enclosure, which is H over L, is 25. It fits in that range of H over L. It's not too tilted. It's just tilted enough, and so you check that angle. And when you use that equation, checking it, the only thing that I don't like is that the Prandtl number is listed. I believe that the Prandtl number is from 1, but our Prandtl number is 0.70, but there's no alternative. Okay. So we use that equation to get a Nusselt number, an average Nusselt number for the enclosure based on the length scale thickness between the two sides of same temperature, which are our cover and absorber plate. You get a 4.19. And so then you get an H is Nusselt K divided by L. And then that comes in at almost 2.965 watts per meter squared degree C. And then Q double prime convection is just the H bar times the delta T. And it comes in at 133.4 watts per meter squared. So this one comes in, well, we gotta write it like that. The radiation is 100, and the convection is 133.4 watts per meter squared, giving us a total rate of heat transfer is 234 watts per meter squared, which is the final answer that we were asked to calculate. Would it pay to maybe seal it and pull a vacuum and diminish that? Yeah, you would cut down on over half of that the convective transfer in that enclosure.